All right, the first thing we're going to do in a problem like this is probably get some totals together because we'll need those. So what I'm going to do here is just create a little table here. And what this table is going to have is the 3 columns for factor B. So I'll call that B1 and B2 and B3, right? And then I'm going to divide this across and call this A1 and A2. I'm just putting these columns together. And then what I'm going to do is I'm simply going to, list the totals for these guys and then the means. So we'll do both actually. Let me just put them all in the same table just to be neat, So first thing we're going to do is have the totals listed. So if I add up, 3.1 and 4.0, of course I get 7.1, correct? So I'd have 7.1, and then I would have 8.8, that would be the 4.6, the 4.2, and then I would have 13.5, and then coming down here I would have 11.2, and then 5.1, and lastly 5.8. Okay, so now that I have those, the next thing I want to do is then to do the averages. So if I divide these by 2, what do I get? Well, this one would give me 3.55, and again, averaging just because it's got 2 numbers that go into it, right? Of course, 8.8 divided by 2 would give you 4.4, and then we'd have 6.75, and then the 11.2 would give us 5.6. And then the 5.1 would give you 2.55. And then the 5.8 divided by 2 would give you 2.9. So it's a little time consuming to do all these calculations. This is why usually in these sections they use software to do all this. But these means are what we would plot to determine if it appears that there is an effect for both the main effects and the interaction. So here's my little drawing. I'm going to label this axis using B1, B2, and B3. Now this is how they asked us to label the axis. And then for this side we're going to label it just, just the mean. So we'll do 1, 2, 3, 4, 5, 6, 7. So I'm trying to draw it by hand, so I'm trying to be neat as much as I can. So this is 1, 2, 3, 4, 5, 6, 7. And I did 7 because this highest number we have is 7 and the smallest is like 2.5, so I figured 1 to 7 would be a good way to number it. Now for B1, what I'm going to do is I'm actually going to plot all the values of A1 first using B1, B2, B3, and I'm plotting the means here. So I'll do 3.55 first. So coming up here, 3.55 is maybe right there. And then I do the same for B2. But it's 4.4 then, so maybe I'm up here a little bit. And then for the next one, 6.75, I come up and maybe I'm there, right? Okay, so let's connect these dots. So there's the first list of values, right? So 6.75, 4.4, 355. Now that's going to be level 1 for factor A, right? Now let's go ahead and do the same for level 2. It'll be 5.6 for the first one. So maybe that's about here. I'm going to draw that as a triangle as best I can. So there's my triangle. And then I'll have 2.55 for the next factor. Notice that this is going to cross here when I connect. That's important. And then B3 is going to be 2.9. So maybe that's around here or so. Okay, so when I connect these guys, it's important that there is an intersection here. Intersection, remember, means interaction. So if these lines were parallel, right, if they were parallel to one another, that would imply there's no interaction effect. The fact that these actually touch one another, cross each other, that indicates there's an interaction. So it could be that the interaction is significant. So this is level 2A. Okay. now once I have that done, my next step is to actually run a standard ANOVA CRD experiment, but I have to treat, you know, this as if it's all just a treatment. So I'll pretend like there's, you know, we would call them A times B treatments, or in other words, I'll pretend like there's 1, 2, 3, 4, 5, 6 treatments using these individual cells, right, where we have these replications. Each one of those is like a separate treatment, and I'll run the typical ANOVA CRD experiment. So that means I need to come up with all these values, like the correction factor, you know, the sum of squares total, all those things I need to come up with. Correction factor is just the sum of all these guys, and then we square that number and divide by the number of values that went into it. So I've actually worked out the sum just for us to make it a little faster. The correction factor, the sum for that is going to be, let's see, I think it's 51.5, which we would then square, and we would divide that by the number of values we have, which is 12. And when you do that in your calculator, you'll see that you get 221.02083 repeating. Okay, so that's your correction factor. Then from there, what you're going to do is to come up with your sum of square total. And the way you do that is you're actually going to square every single value you have. And once you have them all squared, you'll add them up and then subtract off the correction factor. So let me tell you what that works out to be after doing that. Again, so same formula for sum of square total that we've always used. So we just square every value and add them all up. So when you do that, you're going to end up with 249.07, and you're going to subtract off the correction factor of 221.02083 repeating. And you get 28 in that case, so we'll end up having 28.04916 repeating. Okay, so that's your result for that value. That's your SS total. Total sum of squares. Okay, now from here, what I'd like to do next is to simply come up with your sum of squares for the treatments. So sum of square for treatments here is going to be a little bit time consuming, but essentially what we're going to do is to take the totals for each little cell, and that's why I did the totals here, and then we're going to square those and divide by the number of values that went into the total. Just 2 values went into each of these totals, right? So it'd be 7.1 squared divided by 2, then it'll be 8.8 squared divided by 2, plus 13.5 squared divided by 2, plus 11.2 squared divided by 2, plus 5.1 squared divided by 2, plus lastly 5.8 squared divided by 2. And remember, we always subtract off our correction factor. Okay, so let's see what this works out to be approximately. And when you're done, you get an answer of 26.574 approximately, right? So 26.574. So 26.574, and then it goes to 1.16 repeating. But this key value here is our SST. Now, from there, we want to get our SSE, and to get SSE, remember we use this trick with subtraction, so we do SS total, and we subtract off SST, and that gives us the answer for SSE, sort of with a backdoor method there. So 28.04916 repeating minus 26.57416 repeating. And that'll give you, we end up with 1.475. So 1.475. Okay, so that becomes our sum of square for error. Now, once you have the sum of square for error and you got SST, you can then form the MSE and the MST in order to run your test stat. So I'm just going to write down what MST would be. So MST is the SST value of 26.57416 repeating, but you will divide that by the number of values that, or the degrees of freedom, pardon me, for the treatments. So in this case, the degrees of freedom for treatments is just going to be the number of pairs that we had, or the number of these totals that we had, minus 1. So we have 6 of them, minus 1. It's going to give you 5. and then that'll give us your MST. And when you're done, you get 5.31483. And then from there, we can get our last value, which is the last needed value here, which is MSE. So MSE in this case is going to be our SSE, which is just 1.475. And then we're going to divide by the degrees of freedom for the error term here. So what you want to remember here when you're looking at this piece, the degrees of freedom for the error term is basically similar, it can be calculated in a similar way to the sum of squares. We'll take the total degrees of freedom, which remember would have been 12 numbers here minus 1, which is 11. And from there, we'll subtract off the degrees of freedom for the treatment. So we just said the degrees of freedom for treatment was 5. So that means we end up having 1.475 divided by 6. And when you're done, you get approximately 0.24583 repeating. That's your MSE, and here's your MST. Okay, now we know what we have to do there. We finally just divide these two numbers to get our test stat F. So last step here to run this test is to divide these two numbers to get a test stat called F. So 5.31483 repeating divided by 0.24583 repeating. So you get a pretty large test stat. You get 21.620. So 620. And that makes it appear that it's going to be significant. How do you know? Well, you have to compare it against a critical value. Your F critical value that you would compare it against, that's going to have the degrees of freedom that you had here for these two. So it'll be 5, 6. So it'll be F. And let's say you want to test that at the, I don't know if they gave us a significance level in the problem, but let's assume they gave us a 5% significance level. It'd be 0.05, with 5, 6 degrees of freedom. Again, 5 because that was the denominator for MST, and 6 here for MSE. So this is the critical value you would look up and compare this against. But either way, 21.620 is probably going to be pretty large, and so I don't think we need to worry about whether that's significant or not. Okay, so assuming that that is a significant test stat for the treatment effect, that would imply that there is a treatment effect and that we can go ahead and go forward with the test. So as long as we're able to reject the null hypothesis because this test stat is larger than our critical value from the table, we can then move on to the next procedure that we should do. And the next procedure to do is to split up the sum of squares a little bit differently. We're going to take this treatment effect and break it up into its constituent parts. And those parts are going to be the main effect for A, the main effect for B, right, for factors A and B. And then once you're finished with those, you're going to go ahead and do the interaction effect. Now, the first hypothesis test you conduct once you've isolated everything in that way, the first test that you conduct is the test that looks at the interaction effect, because we want to know if there's an interaction before anything. If there's an interaction, we don't bother to test the A and B factors separately. We just skip that step. So we really want to pay attention to whether there's an interaction effect. If there is no interaction effect, then we would go on to test the main effects. So it's pretty straightforward. You test it first to see if there's a treatment effect. If there is a treatment effect, because this rejects the null hypothesis, you next partition the data a little differently into an ANOVA table that has the factors A and B separated out of this term, along with the interaction effect separated out of this term. Once that's all taken care of, you then go ahead and run a hypothesis test on the interaction effect. Because if there's an interaction effect, there's no need to test the separate factors A and B separately because they're interacting together. So you test the interaction effect. Once that's been tested, you're basically done. If the interaction effect is not significant, then you can go ahead and test the individual factors separately. Okay, so we're going to do this ANOVA table breakdown, but in order to do that ANOVA table breakdown, we're going to need to kind of set it up over here and maybe take advantage of some of the things we've already done, right? So hopefully I'll have space to do this. Let's use this as our sources, right? As our sources. Okay, so we're going to have for our sources, sort of the treatment A, treatment B. Then we'll have the interaction between those two terms. And then we'll have the error term. And then, of course, as always, the totals, right? Okay. After we have that, we're going to have our degrees of freedom, right? Our degrees of freedom. So degrees of freedom. Then, you'll have your sum of squares. You need more space for the sum of squares, so leave some space there. Then you'll have your mean squared values. And then finally, you will have your F test stats, right? Okay, so that's basically how we'll break up our table. Pretty similar to what we did before, except for this single treatment effect is now split up into its 3 constituent parts, right? And again, try to make this table nice and neat. Okay, so let's talk about the degrees of freedom first. The degrees of freedom for A is pretty simple. If you're breaking up into its separate parts, there are only 2 levels for A. So the degrees of freedom is just 2 minus 1 here, because there's 2 levels. Take 1 away from that, you end up with just 1. So the degrees of freedom for A is simply 1. Now the degrees of freedom for B, there are 3 factors for B. Take away 1, you end up with 2. And then we'll look at the total interaction and the total value and the interaction effect. So for total, let's do that one first. That's really easy. Of course, you know that if there are 12 numbers in the table, take 1 away from that, you get 11, right? And to get the interaction, you have to use a slightly different idea here. The degrees of freedom for interaction, it's easy to remember this in a way. You can think about it as just the product of these 2 things. It's just the degrees of freedom for A, degrees of freedom for B multiplied. So that's kind of nice. And one way to think of it, I don't know, when I think of interaction, I always think of them crisscrossing, and the crisscross finally makes like a multiplication symbol. So that helps you remember the formula is just the product of the 2 degrees of freedom here. So 2 times 1, or in other words, 2. Now, from there, you end up counting up that this is 5. That means the error term has a total degrees of freedom of 6. Okay, so sum of squares for A, sum of squares for B. We actually have to work that out, and we have to split that up, because right now it's all lumped into this term here. So we have to divide up this quantity so we can get all those values. That's going to be a bit time consuming, so we'll just have to do it. There's no way around it, but it's not that bad. But we'll do that. And then you have the error and the total degrees of freedom. So we have the total sum of squares. The total sum of squares we've already done, so we can just fill that in, right? That part we've got, that doesn't actually change, so that'll be good. That's one thing that's nice. That doesn't change. The error, the error actually doesn't change either, so we can use the error and we don't have to correct that. It's just plug it right in here. So we've got the total sum of squares, got the error sum of squares. Now we just need to break up this 26.57416 repeating into these 3 remaining pieces. We've got to, go ahead and divide that up. So how do we do that? Well, first thing you can do is to come up with the value for A. Now, how we're going to do that? Well, it's just basically if we treat these like, it's a standard SSA, we would then get the sum of the first level, square it. So sum of the first level, square it, and divide by the number of values in that level. Now, there's 6 values in that level. And then you do the sum of the next level squared divided by the number of values there, and then minus your correction factor, right? So that's basically the idea. Now, I've actually already done those sums of those values there just to make our lives easier, because otherwise it takes too long to do. So it'll be 29.4 and 22.1. Square those numbers, divide by 6, etc. Subtract off your correction factor, and you will end up with a value of 4.44083 repeating. 83 repeating. So that's your SSA. So you'll have 4.4483 repeating. Okay, so that's your degree, that's your SSA. Degrees of freedom just means is just 1 there, so 1 divided into that will give you the same MS. But anyways, let's go on to step B now. B is the same thing really, right? But you're going to be summing up these 4 values, squaring it, dividing by 4, these 4 values, squaring it, divided by 4. So when you actually work out SSB, it's going to be very similar to SSA, each one divided by 4, because every one of these columns, right, there are 3 fractions here, and they're going to be made up of those 4 values. So you get the totals, square it, plus totals, square it, etc. And then minus your correction factor. So let's put in these numbers. Now, again, I already did that just to make our lives easier. It'll be 18.3, the first total, then 13.9 for the second total, not turtle, and 19.3. When you finish calculating that and doing your squaring and correction factor, you get 4.126 repeating. So it ends up being 4.126 repeating. So that's what goes here. 4.126 repeating. Now, what's nice is that, we could work out the interaction calculation, but we don't really need to do that now because we know that it has to add up to this quantity. It has to. So all we have to do is take the difference, right? So what's the difference between these 2 numbers and this number? And that gives us our leftover amount. That has to be the interaction amount. And that's a lot faster than doing it the other way. So 26.57416 repeating minus the 4.44083 repeating and minus the 4.126 repeating. And when you're done, you end up with an answer of 18.007 or something, right? So it basically works out to be 18.007. Okay, so now you have that all filled in, you're basically ready to run your stuff. So if you put 1 into here, of course, you get 4.44083 repeating. If you put 2 into this one, you end up with 2.063 repeating, so 2.063 repeating. And then 2 into this one, of course, will give you 9.0035. Let's just put 35, something like that. And then you have 6 into 1.475 gives you approximately 0.24583. Okay, and then from there you just do your ratios. So you're literally just going to put your error into each of these pieces, right? Error into this value will give you this F test stat, and that F test stat, when you work it out, let's do it now. If you have 4.44083 repeating and we divide by 0.24583, we end up with 18.06, etc., right? So let's just call it 18.06 for good round numbers. 18.06. And then if you put this number into this value here, that'll end up giving you approximately 8.39. And then you put this number into here to get your last value. And so you'll end up with 36.32. 36.62, pardon me, not 32, 62. All right, once you have that number, then you would, these pairs of numbers, you would then use your critical values. So the critical values that you're going to have to look up for this one would just be, and again, it depends on how you want to run the test. If you're running it at 0.05, then you're either way, so that's your significance level. But then once you do that, the degrees of freedom, well, think about how you got this 36.62 value. You divided this number by this number. That means you have a 2,6 pair of degrees of freedom, 2,6, right? So use that, look that up on the table, get your critical value, and then make the comparison. I believe 36.62 is going to be large enough to make a rejection. So you will say that there is an interaction effect. That means you don't really need to test these other ones, but if you wanted to look up the critical values for those, you'd end up having, F would be 2,6 again for that one, again 0.05, 2, 6, and then for this one, obviously it would be 1 divided by 6, so 0.05 degrees of freedom 1,6. So you don't need to test these two though, because we can see that there's an interaction effect. If you can look at this critical value, go get the critical value from your table, check it against this. If you reject that, it means the interaction is significant, and at that point you would need to, if you want to go further than that, you would just run a multiple comparison procedure comparing each little individual A-B pair, comparing, factor level B1, A1 against all the other factor levels that there are, and B2, A1 against all the other factor levels there are that you haven't compared to already, etc., etc. That is something, though, you do with software, which is be too time consuming to do by hand. So ultimately, that's the idea of this procedure. And, just to summarize, remember the overall idea is do a graph, just to tell if you see any interaction effect, or if you can tell whether the means are significantly different from the drawing. Once you do that, you run a standard completely randomized design, and the main thing here is that you just lump all of the values together as if it's one sum of square treatment. So you saw how we did that, right? Each individual total became its own little treatment, divided it by 2, squared it, divided by 2, so I ended up with 6 of those. You'll have as many as there are, factors multiplied together. So if there's a 2 by 3, you'll have 6 of them, right? If it was a 3 by 3, you'd have 9 of them, etc. So it adds up pretty quickly. Once you get that done, if that's significant, then you can move forward with the testing, because there's something about the treatments is significant. At that point, you would break it up into an ANOVA table, test the interaction first. If this interaction test stat is significant, you don't need to go any further, you're done. If this interaction is not significant, then you would move on to testing these individual pieces using these critical values, and at that point you would make your decision as to whether A was significant or B was significant, or perhaps both are significant. But that would only be necessary if the interaction effect isn't significant. If the interaction effect is significant, you don't need to worry about that. So ultimately, that's how you do this. These problems are very long, very time consuming, as you can tell.